talk about these faults of every system. As we know, every system has their own faults. For power system faults, it may be categorized as one of four types. First, there are single line to ground fault. Second, line to line fault. Third, double line to ground fault. And fourth, balanced three-phase fault. For the first three types, which is single line to ground fault, line to line fault, double line to ground fault, there constitute several unbalanced operating condition which involves only one or two phases, hence referred to as unsymmetrical faults. For the fourth types, which is balanced three-phase fault, which is involving all three phases, occurs therefore referred as symmetrical or balanced fault. Let's talk about the rotor angle. The rotor angle depends on the balance between electromagnetic torque due to the generator electrical power output or mechanical torque due to the input mechanical power through a prime mover. If in some generator the balance between electromagnetic and mechanical torque is disturbed, this will lead to oscillations in the rotor angle. So the rotor angle stability is further classified into small disturbance angle stability and large disturbance angle stability. And this is classification of power system stability. Previously, I already mentioned about the large disturbance stability and small disturbance stability. For power system stability, it divided into three stability, which is rotor angle stability, frequency stability, and voltage stability. Rotor angle stability involves small signal stability and transient stability. For frequency stability, it only involves large disturbance stability. But for voltage stability, it involves large disturbance stability and small disturbance stability. Objectives for this project is to analyze the power system faults by using the fault technique based on balance and unbalance. Second, to propose suitable protection scheme that for the power system to delivery and sustainability for the given cases. Third, to model a system model for power system using MATLAB. And our scope is by using the MATLAB R2013B, the response of all generators are being stimulated. The simulation model is modeled for transient stability analysis of the system. Third, the stimulation of the system will show the phase angle and the critical clearing time for the system.
Assalamualaikum warahmatullahi wabarakatuh. My name is Izwan Fitri bin Abdul Rahim. I will present about the methodology. So, methodology is the systematic, theoretical analysis of the method applied to a field of study. It comprises the theoretical analysis of the body of methods and principles associated with a branch of knowledge. Typically, it encompasses concepts such as paradigm, theoretical model, phase, and quantitative or qualitative technique. A methodology does not set out to provide solution. It is therefore not the same as method. Instead, a methodology offers the theoretical underpinning for understanding which method, set of method, or best practice can be applied to a specific case. For example, to calculate a specific result. So, in our project, we have used MATLAB software as the software to simulating our project. MATLAB M5 enables a user to perform short-term and small signal stability analysis without adding any new models. So, by following a set of rules, user can assemble customized models and applications since the complete code is in the form of MATLAB files. This toolbox is a standard tool for researchers in power system to analyze power system stability. So we use MATLAB as our software.
Assalamualaikum and a very good morning. I am Muhammad Haris and I will be presenting about the flowchart of obtaining critical clearing time. So first of all, we run the MATLAB software and then we insert the data of 50M and SCMU source code, and then followed by find the time for clear fault and clear remote. So we have used three types here. The first one is without PSS, which is power system stabilizer, and AVR stands for average voltage regulator. So without a PSS, and then with AVR only, and then with PSS and AVR. So after these three types, we stimulate the graph, and finally we got the result for three of them.
Assalamualaikum. My name Muhammad Zulfadili bin Zainuddin. So I will present about result and discussion. Okay. This part we discuss non-bolt fault at bus 33 and 37 is considered as disturbance. Here forecast we to demonstrate the system responses following the fault in the system. There is a stable case, critically stable case, critically unstable case, and unstable case. Okay. This is about the source code for the power system stabilizer, PSS and ESC. PSS is mean the power system stabilized, and ESC is mean the excitation system. Both of them is about stabilize the system. Okay, for stable case, the figure of power grid with PSS plus AVR. So in MATLAB, we set the clear fault and clear remote 1.01 and 1.02. So the figure 1's voltage magnitude in PU versus time in second. So the fault occurred at 1 second and back to normal. After 0.01, a clear fault and the voltage is back to normal again. So the figure 2 is about the generator angle in degree versus time in second. So this show similar time trend of generator swing and unison as well. So the figure 3 is about the oscillator is damping. Okay. The second, the power grid without PSS and AVR. So we set in the MATLAB, clear fault and clear remote is 1.01 and 1.02. So the figure 1 is voltage magnitude in PU versus time in second. So the fault occur at 1 and back to normal again. So the figure 2 is angle in degrees versus time in second. This is a similar time trend of generator swing in unison as well. And about the figure 3, speed in period and time in second. Yeah, the oscillator is damping, but there is generator. The speed of generator is not balanced at all. So this is a figure about power grid with AVR only. Clear fault and clear remote is 1.01 and 1.02 in MATLAB. So the figure 1 is voltage magnitude in PU versus time in second. So the fault occur at 1 second, and after 0.01 the clear fault and the voltage magnitude is back to normal. And the figure 2 is about the generator angles in degree versus time in second. So that show the similar time trend of generator swing in unison as well. And the figure 3 is about speed of generator in PU versus time in second. So the oscillator is damping, but there is need more time than with the power grid with PSS and AVR. It's constantly decrease the speed of generator. Okay, the critical stable case. Okay, the PSS we start with PSS and AVR, the clear fault and clear remote at 1.49 and 1.50 in MATLAB. So this figure 1 is showed about voltage magnitude in PU versus time in second. The fault occurred at 1. After 0.49 second, the voltage increased instantaneously, and then that stabilized the voltage, maintain the voltage after 4 seconds. And then about figure 2 is the generated angles in degree versus time in second. The generators is increase, the angles of generator increase after 1.5 and decrease after 4 and get to normal again, is maintained. And the figure 3 is about speed in PU versus time in second. So the generator is not same, but it's success to get back the power grid stable. So the figure, this is a figure power grid without PSS and AVR. So we set the clear fault and clear remote 1.25 and 1.26. So figure 1 show the voltage magnitude in PU versus time in second. There is the fault occurred at 1, and after 0.25, the voltage is increased to maintain the voltage in the power grid. And the figure 2 is show angles in degrees of generator versus time in second. The angles increase after 2 and decrease after 3. That's capable to maintain the angles. And about the speed of generator versus time in second, there is a very increasingly of speed of generator after 1.2 something and start to decrease and to achieve the stabilize in power grid. For the power grid with AVR, clear fault and clear remote we set in MATLAB is 1.30 and 1.31. So the fault occur at 1 second, and after that, after 0.30, the voltage increasingly to get maintained back. And the figure 2 show the angles in degree of generator versus time in second. It's not the time trend of generator swing, not in reason as well. About the figure 3 speed in PU of generator versus time in second, there is generators is not balanced at all. It just speed is not balanced. About critical unstable case, figure of power grid with PSS and AVR, clear fault and clear remote we set in the MATLAB is 1.50 and 1.51. So the fault occurred at 1, and then after 0.50 is capable to maintain the voltage magnitude in PU, but there is a little noise. And the figure 2 is show the angles of generator in degrees and time in second. After 1 after 1.50, the generators of angles increase instantaneously. Uh, at the 10 second, it reach about 60,000 angles, 60,000 degree. So the figure 3 is show about the speed in PU of generator versus time in second. So this we can see the generators is increase, and now there is the speed of one generator is 0.11, and there is to maintain the fault occurs, and then the generators the generator S, another generators is capable to maintain the fault. The figure of power grid without PSS and AVR, the clear fault and clear remote we set 1.26 and 1.27. So the fault occur at 1, and after 0.26 the voltage increasely to maintain, and then it's, after 5 seconds, after 6 seconds, the voltage is decrease. It's not, this is to reach to get the fault again. The figure 2 is show the angles in degree versus time in second. After 6.5 seconds, the generator angles increase, and the figure 3 show the speed in PU of generator and versus time in second. After 6.5 second, the speed of generator is increased, and one of the higher of generator, at the 10 second it reach 0.45 PU speed. For the figure of power grid with AVR only, clear fault and clear remote we set in mallet is 1.31 and 1.32. So the figure 1 shows the voltage magnitude in PU. There is and the versus time in second. So the fault occur at 1. After 0.31, the voltage is increased, and to maintain the voltage, why the figure 2 show the angles in degree of generator versus time in second. After after 3.5, the angles increase about to 12,000 at 10 second, and the figure 3 is show about speed in PU versus time in second. So we can see here the only one generator and they're capable in higher speed. There is 0.11 PU, and then the all generator beside, except this is capable to maintain the clear fault. For the unstable case, so the power grid with BSS and VR, clear fault and clear remote, we set in MATLAB is 1.52 and 1.53. So the fault, this figure 1, the fault is occurred at 1 second. After 0.52, the voltage increase, and and get to maintain the power grid again. And the figure 2 is show the angles in degree a time a second. Then 1.5 the angles of degree increase about the 17,000 degree at the 10 second. So the figure 3 is show about the speed in PU of generator versus time in second. So we can see here the only one generator this operation in higher speed. Then all generator except this one generator is maintain the system. So the figure of this is a figure of the power grid without PSS and AVR. So we set in MATLAB for the clear fault and clear remote is 1.27 and 1.28. So the fault happened at the figure 1 is the fault is occurred at 1 second, and after 0.27 the voltage increased, but after 3 after after 2 I'm sorry after 2 the voltage is decreased because it's not capable without the PSS and AVR. It's not capable to maintain the voltage, and it get to fault again. Figure 2 is showed about the angle in degrees and versus time in second, and this the angle of generator increase after the 4 second and get to and all of generators increase, and the figure 3 is showed about speed in PU versus time in second, and the speed is increased after the 3 second, and the height of generator is about 0.8 something that to maintain the power grid. So the figure of power grid is with AVR only clear fault, and clear remote is 1.32 and 1.33 in MATLAB. So the voltage magnitude is in PU versus time in second, and then the fault occurred at 1 second, and then after 0.32 second the voltage is this back to normal and maintain the voltage of power grid. And the figure 2 is show angles in degrees versus time in second. For the angles of generators is increased after the 3.5 second about 13,000 degrees, and the figure 3 show the speed in PU and versus time in second. So we can see only one here. The generators is operate in higher speed, and the other generators capable to maintain the clear the to clearing fault. So we can see here, we can conclude the system, the power grid with the PSS and AVR is more efficient than the AVR only and without PSS and AVR. This is because the PSS and AVR can maintain the generator speed that capable in the right way than the AVR only. However, AVR is capable to maintain the speed of generator to clear fault, but it's consume plenty of time. Without the PSS and AVR, is difficult to get back the fault, and it maybe can get the maintain the power grid uh, back to normal again. So last but not least, so again I say the power grid with the PSS and AVR is efficient and better than AVR only and the AVR and PSS. That's all. Thank you.
From this project, we conclude that we can learn and understand about the faults in power system, also the importance of stability. And then second, we also learn and understand how to use MATLAB for this project. And third, we gain three results from three conditions, which is without AVR and PSN, with AVR, and with AVR and PSS. And the results show that the graph for the phase angle, rotor angle, and rotor speed, and what time the system in the stable condition and unstable condition. That's all from us. Thank you.